Sound check one. Sound check two. Okay, I think we're good to go. Good morning. This morning we're going to talk about applications involving exponential growth and decay. And the first application is going to be compound interest formulas. And because we're solving applications where the variable we're looking for is going to be in an exponent, these are going to be exponential equations, and we're going to use logarithms to help us solve them. So as I'm talking, please feel free to ask questions in the chat bar. There is a bit of a delay between when I speak and when you hear me, so don't be discouraged if I don't respond right away, and I will be getting to your questions. About what we're talking about or other things. So I know as we finish up the semester, you have, you're reviewing for finals and everything. So if there's something else you want to ask about, just let me know and we'll see if we can fit it in. Okay, so let's go ahead and get started with the first application. Compound interest is a topic that we all experience actually all the time. Compound interest is usually how they calculate interest on, for example, your credit cards. And the way that it works is instead of just adding, let's say the interest rate is like 10% per year. Instead of just adding it 10% at the end of the year, they add it on intervals. And it has this interesting effect because every time they add in part of the interest, then on the next interval of time, they add interest to the interest. And then on the next interval of time, interest to the interest on the interest. So that's why it's called compounded. And that's also why it has an equation or formula that is in exponential form. So the way that it works is we have the formula, which you can see here on the screen. A equals P times 1 plus R over N to the NT. Let me see if I can highlight that. That would help if my pen were plugged in. Hold on just a second. There we go. All right, so this is the A equals P times 1 plus R over N to the NT. And we need to know what each variable represents. So A is the accumulated value of the money that you either invested or maybe owe if you're talking about a debt like a credit card. And then P is the principal or starting amount of the money. T is the number of years that this interest is accumulating. So T is time, but always measured in units of years. And then R is your annual percentage rate. And you always plug in the percentage rate in decimal form, not percent form. And then finally, here's where the compounding comes in. This interest is going to be calculated N times per year. So just knowing your interest rate is 10%, for example, isn't enough to know how much interest is actually going to accumulate, because the more times a year that you add on the interest, then the greater amount of interest you're going to end up with because of the compounding effect. So, for example, 10% 4 times a year means really you're going to add 2.5%. 10% on intervals of compounding intervals of 4 quarterly is what we call it. You're actually going to add 2.5%, a quarter of 10, 4 times a year. So in the end, you end up with more than the 10% of the interest being added on. Okay, so let's look at a particular example where we're given the amount invested, the number of compounding periods, the annual interest rate, and the accumulated amount, and we're asked, we're asked to find t in years. So what are they telling us? They're telling us the principal p, they're telling us the number of compounding periods n, they're telling us the annual interest rate r, although we do have to convert that to decimal form. So we're going to move the decimal place 2 places to the left. And then they're telling us the accumulated amount in the account at the end of the time period of the investment A. And a lot of times in other books they refer to this, by the way, as the future value, and they refer to the principal as the present value. So you'll see that sometimes. Anyway, we're looking for the time t in years. So each time you work one of these problems, go ahead and write out the formula A equals P times 1 plus R over N to the NT. And we're going to plug in each value. So A is 21,000. P is the principal, which is 11,000. You don't have to put the dollar sign, but. And then times 1 plus R is 0.0525 over N is the number of compounding periods, which in this case is 2, excuse me. So you might see them explain that same scenario as compounded semi-annually. In fact, let me go ahead and list, before we continue with this problem, the various compounding periods and how they may be given to you. So you might have a compounding period that's indicated with the word annually, and that means your n value is 1. Semi-annually means twice a year, so n is 2. Quarterly means 4 times a year, so you're going to use n as 4. Monthly is another common one. That's 12 times a year. It might be weekly, which means that it's going to be 52 because 52 weeks in a year. It might even be daily, which means 365 times in a year. But this one, they actually told us the n value is 2, and then we're going to raise it to the 2 times the number of years, but we don't know that, so we're going to call that t. Okay, so now what we need to do is we have an exponential equation. That just means that the variable is in the exponent. And whenever you have an exponential equation, you want to isolate the exponential expression, which is this whole part that's being raised to a power. So we want to get this part, the exponential expression, by itself. So I'm going to divide both sides by 11,000, right? This 11,000 is being multiplied, so we're going to divide on both sides. Get a different color here. How about blue? So we're going to divide both sides by 11,000. Now when we're doing this, we're not actually going to plug anything into our calculator until the very last step. Why? Because when we're talking about people's money, they don't want any rounding off errors. They want every penny exactly correct. So you're just going to leave the left side as 21,000 over 11,000, or without a calculator, you could actually reduce that, right? Divide by 1,000 and it's 21 over 11. equals 1 plus 0.0525 over 2 to the 2t. Okay, now another thing I like to do, and this is totally optional, is I don't like to leave the base of this exponential expression as a sum. I like to actually add these together because it's really easy to do. So in this case, all you would do is get a common denominator of 2. So you write the 1 as 2 over 2 and add that together. So you'd have 21 over 11 equals, and then it's just going to be 2.0525 over 2 to the 2t. Now, when the denominator is only has factors of 2 or 5, you can actually go ahead and divide that because you'll get an exact answer. But when the denominator has any other factors, like let's say it was monthly, so the number 12 has factors of 2 but also a factor of 3. So division would result in a not exact answer, so you would not want to divide that. So when you have other factors, don't divide because you won't get an exact answer. You'll have a round off error. So that's why I'm showing you writing it as a fraction like that. If you're wondering, like, I'm not trying to overcomplicate it, but if this denominator had been, say, a 12, you would not want to divide it out because you'd have a round off problem. Okay, anyway, so I'm going to leave it written like that just so you can see how it works when we don't divide it out. So we're going to have to now figure out a way to get the variable out of the exponent. And the way that we do that is using a rule of logarithms that we discussed in class, which said that when you have the log base, any base b of m to the n power, that's the same as n times the log base b of m. In other words, you can always bring the power out front of a log. So we're going to take the log of both sides of this equation. So I'm going to have the natural log of 21 over 11 equals the natural log. We use natural logs because it's the log, one of the two logs on your calculator. You could use log base 10, the common log as well. But usually we just use the natural log. Okay, so this, now that we've taken the natural log of both sides, we can bring this power 2t out front. So we have the natural log of 21 over 11 equals 2t times the natural log of 2.0525 over 2. Okay, and now we just have to divide to get t by itself. T is being multiplied by the 2 and by that logarithm. So we're going to divide both sides by the 2 and by the natural log of 2.0525 over 2. Okay, so that means that t, everything else cancels out, right? Divides out to be 1. So that means that t is equal to the natural log of 21 over 11 over 2 times the natural log of 2.0525 over 2. Okay, so again, we wait till the last step to plug into our calculator just so we avoid any round off errors. But then you got to be careful about how you enter this into your calculator. First of all, whenever you have operations going on in a denominator, you need to make sure to use an extra set of parentheses in order to enter this with the correct order of operations. And so let's go ahead and do that. Get out your calculator at home if you haven't done so already. And we're going to type in the natural log, parentheses should pop up. You're going to do 21 divided by 11, close parentheses, and then you're going to divide that by parentheses 2 times the natural log, parentheses, 2.0525 divided by 2. Oops, went too far. Sorry, guys. Close parentheses, enter. Okay, so I'm going to do the same thing here at my desk. Natural log 21 divided by 11, close parentheses, divided by parentheses, 2 times natural log 2.0525 divided by 2, close parentheses, and we get that t is approximately 12.5 years. Oops. Sorry. There we go. 12.5 years. Okay, so just check to make sure that you can get that value on your calculator. All right, those are my students who are watching. Remember to type your name and the days and times of your class into the chat bar. It should be my Monday, Wednesday, 9:30 class, but if other college algebra students wanted to pop in, you could do that as well. All right, so any questions, remember you can type that into the chat bar as well. So hopefully everybody's doing okay so far, but don't hesitate to stop me if you have a question. All right, so we're gonna now look at a different scenario for compound interest. We talked about annually, semi-annually, quarterly, monthly, weekly, daily, right? But what if we had a compounding that occurred every minute, every second of every day? It just was constantly compounding, like an infinite number of times per year. So it turns out that when you let the value of n get extremely large, going towards infinity, that you end up where the formula actually changes and it starts to look like A equals P times e to the RT. And I don't know if you remember, but e is just a number like the number pi. It's an irrational number. You can't write it its exact form because it's a non-repeating infinite decimal, but it's about 2.71 or 2-ish. Okay, so this is not a variable in this formula, it's a constant, but it's being raised to the power RT. So we can end up, again, if we're solving for the amount of time it takes for some money to accumulate, we can end up with, or the rate for that matter, you can end up with an exponential equation and you solve it using logs. So again, the variables represent accumulated value A, P is the principal, after T years at an annual percentage rate of R, and then it'll say compounded continuously, and that's how you know that you're using the PERT formula, A equals PE to the RT. You'll notice there's no N, no compounding periods, because it's being compounded continuously. So let's use this idea. Oh, I thought I had a problem on here. I know I did at some point. All right. So I'm going to just make one up then. So suppose that we started with a principal of $5,000 and we want to know when can we get 10,000 if we have an interest rate of 6%, so 0.06, and it's compounded continuously. So we're looking for how long it's going to take basically for our money to double. This, by the way, is often referred to as doubling time when you're looking for the time it takes for money to double. Interesting thing about compound interest is that it takes the same amount of time for $1 to double as it does for $1 million to double, which is why money tends to kind of accumulate into a small number of hands in society. So anyway, we're going to plug in and we're going to have 10,000 equals 5,000 times e to the, remember e is not a variable, that's the value itself, you just leave e in the equation, 0.06 t. All right, now just like when we solved the previous equation, we want to get the exponential expression, which is, when I say that, I'm referring to the thing being raised to the power there. It's the exponential expression by itself, and the way we do that is the same. You just divide both sides by the coefficient, which in this case is 5,000. This is the step that shows you why doubling time is always the same answer, because no matter what two values we had on either side, if the a is double the p, then this is always going to divide out to be 2 equals e to whatever power. Okay, so now how do we solve this equation? Well, we're going to do the same thing we did before. We're going to take the natural log of both sides. It's very important, though, in this case that it is the natural log, because we want this base e to cancel with the natural log base e. So what I mean by that is, remember, natural log of e to the 0.06t means the log base e of e to the 0.06t. When you have the same base in the exponential expression as in the log, they're going to cancel each other out. So we're going to be left with just the exponent, 0.06t. So we have the natural log of 2 equals, and then we're going to have 0.06t. We're going to divide both sides by 0.06. So our t is going to be the natural log of 2 divided by 0.06, which is approximately what? Let's get out our calculators. Natural log of 2 divided by 0.06. That's going to give us 11.55 years. Okay, so about 11.5 years at a 6% interest rate compounded continuously for that money to double. So if you started with $1 in the account, then at the end of 12 years you'd have $2. If you started with $1 million in the account, at the end of 12 years you'd have $2 million. Okay, so that's compound interest. That's one type of exponential growth equation. But there are many others in various contexts. Oh, you got 3.5? Let's take a look. Oops, wrong page. Maybe I typed it in wrong. No. Make sure, Elaine, that you close the parentheses. So when you're typing it in on your calculator, you should see on your screen natural log parentheses 2, close parentheses, divided by 0.06. Okay? Because the thing is if you type in natural log of 2 divided by 0.06, then it's going to divide the 2 by the 0.06 instead of dividing the natural log of 2 by the 0.06. So this would be incorrect. Okay, so let's look at another kind of exponential growth. The exponential model, a equals 658.9 e to the 0.02 t, describes the population A of a country in millions t years after 2003. Use the model to determine the population of the country in 2003. Okay, so here they're giving us a model. It's a type of model that comes up a lot. And we're going to talk about the form of the model in a minute. But right now we're just going to use it as a formula. So all they're asking us to do is to plug in t. But what is t? So t is the number of years after 2003. So if we're in the year 2003, we're not going to write t equals 2003, right? T is the number of years after 2003. So how many years after 2003 is 2003? 0 years, right? So they're really telling us that it's t equals 0. So we're supposed to plug 0 into the formula. A equals 658.9 e to the 0.02 t. So we have A equals 658.9 e to the, now this is 0.02 times 0, which is just going to be 0. But any number to the 0 power is 1. So A is equal to 658.9 times 1. So A is just 658.9. So, and what did A represent? The population in millions, so millions of people. So this is the starting population in this model. And so a lot of times this number here that's right in front of the exponential expression is called the initial value, because it's the value when time is 0. It's the starting point. So this follows a pattern of an exponential model for exponential growth or decay. So exponential growth would be like populations. They get bigger over time. Decay, well, I mean, obviously populations can decline, but usually they tend to increase. And then decay would be like, a perfect example would be like when they carbon date fossils and stuff. So over time, the amount of certain radioactive substances decays, and they use that as a way of measuring how much time has passed. So in either case, though, you're using this same formula, A equals, and then this is a different variable, not the same as variable A. A sub 0 is the initial value, and e to the kt. If k is a positive number, then we have a growth rate. So when k is positive, this value increases over time. And then if k is negative, then we have a decay rate. And that makes sense if you think about it, because remember when we graphed the functions, say we wanted to graph f of x equals 2 to the x. So this gave us an increasing graph. But if we change the sign of the exponent, let me use a different name. Let's do g of x equals 2 to the negative x. Remember, we ended up with a decreasing exponential function. So this k being positive or negative is going to determine if the function is increasing or decreasing. All right, so for just as an example of some models that you could see here, we have the exponential models describe the population of the indicated country, country 1, 2, 3, and 4. A is in millions, t years after 2006. Which country has the greatest growth rate? All right, so K is your growth rate. So what they're really asking us is just what's the biggest coefficient of t? What's the biggest number here? So we have several growth rates. We have negative 0.009. we have 0.002, we have 0.014, and 0.002. A negative is not a growth rate at all, right? That would mean that the population is actually declining. So this is actually a declining population. Okay, so definitely not the fastest growth rate. But let's compare these other three. Which one is the biggest value? Well, that would be the 0.022 would be the largest growth rate. And one interesting thing about the growth rate is if you wanted to know by what percentage the population of the country is increasing each year, you can actually just multiply the growth rate by 100 to get the percentage. So the percent would be 0.022 times 100% is going to be 0, well, let's just write 2.2%. So the growth rate of that country is 2.2%. Okay, so for a question like this, you're going to need to know that the coefficient of t is your k that represents the growth rate, and that if you multiply it by 100, you get the percent of increase each year. All right, let's look at another model. Here we have the exponential model A equals 81.9 times E. Sorry, I'm trying to grab this and make it a little bigger. It's not letting me here. Let's see. Okay, times e to the 0.029t. It says it describes the population A of a country in millions t years after 2003. Use the model to determine when the population of the country will be 134 million. Okay, so if A is the population in millions, then the information they're giving us here is A, right? Except A is measured in millions, so A is just going to be 134. And we want to find t because it's asking when, right? So let's go ahead and plug in 134 to our model. So we have 134 equals 81.9 e to the 0.029t. And once again, because there's a variable in the exponent, we have an exponential equation, and we want to isolate the exponential expression first. So that means to divide. So it's the same procedure for solving these exponential equations, basically. So we're going to divide by any coefficient. I'm not going to put anything in my calculator until I have t completely by itself, though. All right, so we're going to have 134 over 81.9 equals e to the 0.029t. All right, now at home, answer this question to yourself. What do we have to do next? What is the step that we did when solving the other exponential equations after we divided both sides by the coefficient? So all right, so there's a question, how come you didn't divide the entire thing like the last one? Let me see. What did we do here? Well, not this one, right? Not the one with the one where we knew t, but you're probably talking about the one in the previous page. So let me go back to the previous page. All right, so here on the previous page, you see what we did? We divided both sides by 5,000. So I was doing the same thing here. The 5,000 was being multiplied by the exponential expression. So to reverse that, we divided by 5,000. And really it was the same thing in the previous problem as well. Back in this step here, right, we had the exponential expression being multiplied by 11,000. We divided by that. So it's the same. It's consistent. Okay. So we're going to divide by 81.9, and then we still need to get the t out of the exponent by taking the natural log of both sides. So we have natural log of 134 over 81.9 equals the natural log of e to the 0.029t. We're going to bring the power out front is one way of thinking about it. Or you can think of it as the natural log cancels with the e. Last time I wrote it as natural log canceling out the e, but let me just show you can think of it this way as well. You can think of it as applying the power rule, and that would bring the power out front times the natural log of e, but the natural log of e is just 1, right? Log base e of e. So that's going to be natural log 134 over 81.9 equals 0.029t. We're going to divide both sides by 0.029. So we get t equals the natural log of 134 over 81.9. All of that divided by 0.029. All right, so try calculating that at home using your calculator. What are we going to get? Let's see, we have the natural log of parenthesis, pops up automatically, you don't have to type it. 134 divided by 81.9. You do need to remember to close the parentheses, and then we're going to divide that by 0.029. And so I got approximately 17 years after 2003. So that would mean that the answer is 2020 based on the information given in the problem. Okay, so we expect that population to reach 134 million in 2020. Now, tell me, just looking at the formula, what was the population to begin with in 2003? What's the starting value? Hopefully you said 81.9 million was how many people were there in 2003. You can figure that out two ways. One, you can know that in exponential growth formulas, this is your initial value. And two, you can confirm that by plugging in 0 for t. So this population is growing significantly, right? That's what we refer to as exponential growth. You know, it's a very steep growth. After just a short period of time, it gets very, very large. Okay. Moving on to the next problem. This is a problem you'd see in my math lab. It's chapter 4, section 5, item number 7. It says in the year 2000, the population of a country was approximately 6.42 million, and by 2028, it is projected to grow to 8 million. Use the exponential growth model A equals A sub 0 times e to the kt, in which t is the number of years after 2000, and A sub 0, which, by the way, again, we often refer to as the initial value, is in millions, to find an exponential growth function that models the data. So this time they're giving us information about the function and we're writing the function. And then after that, it asks us a question about it, part B, that we have to answer. But first we have to write the function. All right, so if t is the number of years after 2000, this is really important, because what that means is that in the year 2000, that's our time 0. And they're telling us that in the year 2000, the population was 6.42 million. So automatically, since it's the initial value of the population at time t equals 0, that means that that's a sub 0 in your formula. So you can replace a sub 0 with 6.42. And then we have times e to the k. We don't know the value of k. They did not tell us the growth rate. Times t, which is a variable. All right, so there's got to be, we're almost there, but there's got to be one more piece of information to help us to find the growth rate k. So what else are they telling us in this problem besides a sub 0? They're telling us that by the year 2028, that the population's projected to grow to 8 million. So when they say the year 2028, remember that t is the number of years after 2000. So t in 2028, if you subtract 2000, would be 28. So they're giving us that t is 28 at a particular population level of 8 million. So that's when the accumulated value of the population is 8. So now what we can do is, you see, if we plug in the 8 for A and the 28 for T, then we're only missing the value K, and we can solve for that value. We can find our growth rate. So we have 8 equals 6.42 times e to the 28k. All right, now how do we solve an exponential equation? We first isolate the exponential expression by dividing by the coefficient. So we're going to divide both sides by 6.42. And then we're going to get e to the 28k equals 8 over 6.42. We're going to take the natural log of both sides to get that k out of the exponent. Bringing the power out front, then we have 28k times the natural log of e equals the natural log of 8 over 6.42. But the natural log of e is always 1. Then we're going to divide both sides by the coefficient of k, which is that 28 there. And we're going to get k is equal to the natural log of 8 over 6.42, all divided by 28. So let's plug this into our calculator, and remember, to maintain the correct order of operations in your calculator, you're going to need to put this quotient, the division of 8 by 6.42, in parentheses inside the logarithm. All right, so we have the natural log, parenthesis, 8 divided by 6.42, close parenthesis, and then that number divided by 28. Okay, so I get that k is equal to 0.00786 approximately. Okay, hopefully you got the same thing at home. So that means that we have our formula. A equals 6.42 e to the 0.00786 t. Okay, so that's the answer to part A, the formula. So how did we get that formula? Well, we were given the initial value, 6.42, and then we were given a certain value of A in a certain year. So we were able to plug that in to find K. It's going to be a very similar procedure whenever they ask you to write your own exponential growth equation. Now let's do part B. So for part B, in which year will the population be 10 million? So here, what are they giving us? They're giving us the value of A, the accumulated value, 10 million. So we want to know, when does 10 equal 6.42 e to the 0.00786 t? And actually, I trying to remember, in my math lab they actually wanted you to round off to just 2 decimal places, so let's do that here. We would round off to 0.01 t, just so we get the same numbers. So let's solve the equation. 10 equals 6.42 e to the 0.01 t. And what do we do first? We isolate the exponential expression. So we're going to divide both sides by 6.42. Okay, so that means that e to the 0.01 t is equal to 10 divided by 6.42. Take the natural log of both sides. Oops. That's kind of thick there. Take the natural log of both sides, and we can bring this power out front, and natural log of e is just 1. So on the left we just have 0.01 t. On the right we have natural log of 10 over 6.42. We're going to divide by 0.01, so t equals natural log of, that was supposed to be there, 10 over 6.42 divided by 0.01. So let's plug that into your calculator. Natural log, the parenthesis opens automatically, 10 divided by 6.42, close parentheses, divided by 0.01. So we get t equals 44.3 years. Okay, now in my math lab they want to know in what year, rounding to the nearest year. So remember, the starting year was 2000. T is the number of years after 2000. We're going to round to the nearest year, which is 44. So that's going to give you the year 2044. Okay. All right, so there's a try this problem with the details worked out at the end of this page in your OneNote. So after we finish the live chat, you can go back in and try that and see how you do. But now we're going to move to the next page, which is about exponential decay. So remember, decay is when the quantity that is accumulating is actually declining. Instead of accumulating, getting bigger, we're having fewer of them. So your K value is actually negative. That's your growth rate is negative. So an artifact originally had 16 grams of carbon-14 present. The decay model is A equals 16e to the negative 0.000121 t. This describes the amount of carbon-14 present after t years. use the model to determine how many grams of carbon-14 will be present in 8,015 years. Okay, so this problem is giving us the time in years, and they're asking us to find the amount that's remaining. So it originally had 16 grams. That's why you see the K equals 16 here, the initial value. But they're telling us T, we want to know in T equals 8,015 years, how much will be left. So all we have to do is plug in A equals 16 times e to the negative 121 times 8,015. All right, so let's make sure you can enter this into your calculator and come up with the right answer. So there is an e to the power function on your calculator, but in order to get to it, you have to, if you're using the TI-30X2S calculator, you're going to hit second and then the ln button to get the e to a power. It's going to automatically give you an open parenthesis there. So then you just type in your number and the multiplication, and then close the parenthesis and hit enter or equals. All right, and what you should get is 6 grams, approximately. You're going to round to the nearest whole number. So this is going to be approximately 6 grams. Okay, so let me know if you have any trouble plugging that into your calculator. All right, and I'm going to move on now to a definition. So in some of the problems, it's going to refer to half-life. So you need to know what the half-life is referring to. The half-life of a substance is the time required for half of a given sample to disintegrate. And just like it's this takes exactly the same amount of time for $1 to double to $2 as it does for $1 million to double to $2 million. It's the same thing with half-lives. So it doesn't matter how much of the substance you start with. If you start with 2 grams and you find out how much time it takes to get down to 1 gram, that's the same as starting with 2 million grams and seeing how much time it takes to get down to 1 million grams. So the half-life of a substance can be calculated no matter what starting and ending amount we have, as long as one's double the other. So, but in general, to find the half-life, you substitute the starting value divided by 2, right? If the starting value is 2 million, you substitute in 1 million for A. If the starting value is 2, you substitute 2 divided by 2 is 1 for A. And then you just solve for T using the same techniques we've been using. All right, so it says, here's an example. Complete the table shown to the right for the half-life of a certain radioactive substance. And it's telling us that our decay rate is 4.9% per year, or in decimal form, and taking into consideration the sign of decay is negative, that would be negative 0.049. So let's go ahead and write out the model for exponential growth and decay. And then we're going to put in for K, we're going to put in negative 0.049. Okay, and then to find half-life, whatever our initial value is, we're going to take that amount and divide it by 2. So your A is replaced with A sub 0 over 2. So that's one way to set up the equation, and you can work it out that way because you can divide both sides by A sub 0 and the A sub 0s will cancel out. But I just want to point out that you do have another alternative. Remember I said that it's going to work out the same no matter what your starting value is. So what if I used a starting value of 1? Then my ending value A would be half of that, or a half. So you could also just solve the equation 1/2 equals 1 times e to the negative 0.049t and not have to worry about those variables canceling out. It's just a little cleaner this way. So that's what I like to do. So that's just going to mean that 1/2 equals 1 times anything is itself. So it's just e to the negative 0.049t. And then we're going to take the natural log of both sides. So we get natural log of 1/2 equals the natural log of e to the negative 0.049t. Okay, and then whether you think of it as the bringing the power out front and the natural log of e is 1. Oops, sorry about that. Okay, that's better. Or you think of it as the log base e canceling with the e. Either way, this equation becomes the natural log of 1/2 equals negative 0.049t. And we're going to divide by negative 0.049, and we get t equals natural log of 1/2 divided by negative 0.049. So let's figure out that one on your calculator. You could put in 0.5 instead of a half and make it a little easier. So we have the natural log of 0.5. Close those parentheses on the 0.5 and then divide by negative 0.049, and you're going to get 14.1 years. And let's see, in my math lab, so t is approximately 14.1. In my math lab, they wanted to round to 1 decimal place. Oh, so I did it right. So the half-life that you should give is 14.1 years. Okay. All right, so we're going to stop there. That's our very quick explanation of exponential growth and decay. And I hope you find it helpful. Remember, the notes are in your OneNote folder under the live chat tab. And, or I should say OneNote notebook under the live chat folder. Are there any questions before I sign off today? Okay, so that's it. So for my Monday, Wednesday, 9:30 class, we are meeting on Monday. I want to say it's at 9. Let me just check. Make sure I'm remembering that correctly. We go. Yeah, so in order to not interfere with the final exam schedule, we're going to do 9 a.m. to 10:20 a.m. So I'll see you Monday at 9. We're going to play Jeopardy and get some bonus points and practice for the final. If you've already taken the final at that point, then you'll just be better prepared to earn some extra bonus points. Everyone who participates will get bonus points, but the better your group does, then the more bonus points that you're gonna get. So come prepared. You'll be able to use your notes, but not the internet. Okay, and we'll have a lot of fun. Usually students enjoy it. So I've been doing it for in many classes for the last few years, and we have a good time. So if there are no questions, then I'm going to sign out. Thank you, and have a good weekend. Happy studies. Remember that the tutor labs are available to help you, and there's the STEM Center on the first floor, and then there's a lab where they do no algebra on the second floor as well. So also there's brainfuse.com, which is there's a link in your D2L. So if you are studying in the middle of the night, can't get to campus, and you have a question, you can always use BrainFuse to just live chat with a tutor. Okay, good luck, guys. I'll see you Monday.